Yeah, blocks A and B have equal mass M, and are on a frictionless track. Stationary. Block B is moving toward block B with a velocity. After block A collides with block B, it travels around a circular loop, radius R. It travels around the circular loop, and then slides up a ramp, radius R, and then continues up the ramp until it reaches a height H, the floor where it comes to rest. So we're going to assume the collision between blocks A and B is perfectly elastic. Remember, that's just the same as if it's elastic. That means kinetic energy is conserved. And for these questions, we want to express the answers in terms of V1 and R and any physical constants. So the first part of part A says, what are the speeds of blocks A and B immediately after the collision? So because it's a collision, we're going to set up conservation of momentum. So that's going to be M1, V1 initial, plus M2 V2 initial is equal to M1 V1 final plus M2 V2 final. Remember, because it is an elastic collision, the blocks are not stuck together, so we have two separate terms in the final part. Block B was initially at rest, so we can set this term equal to 0. And the blocks have the same mass, so I'm just going to rewrite this equation as M. V1 initial is just V1 is equal to M times V1 final plus M times V2 final. We have the same M in all three terms, so I can cancel that out. And what this tells you is that V1 is equal to V1 final plus V2 final. So the final velocity of these two blocks combined will be equal to that same initial velocity of V1. So let's say, for example, if V1 was 20 meters per second, V1F and V2F could be like 10 and 10, or it could be 3 and 17, or any combination of two numbers that would add up to 20. So how do you figure out what those two numbers are? Well, that's where you have to set up the conservation of kinetic energy, since you know it is a perfectly elastic collision. So what I'm about to write down, I don't want you to copy this in there because I didn't leave you much space in this question, but also because it's rarely going to show up on the test. It could show up, which is why I want you to see it, but I don't want you to take the time to actually really memorize it unless you're looking to get a perfect score on the AP exam. But I want you to follow it because it does lead to a very important final conclusion about this that I really do want to make sure that you know, because it'll help simplify a lot of questions. So this is still under part 1, and again, don't write this down, just make sure you follow it. We're going to set up conservation of kinetic energy for the elastic collision. So that is going to be 1/2 m v1 squared plus 1/2 m v2 squared is equal to, and those are initial velocities, so v1 initial and v2 initial, that's equal to 1/2 m v1 final squared plus 1/2 m v2 final squared. Notice every term has a 1/2 and an m, so I'm going to cancel all of that stuff out. And also, just like up here, with that, the momentum of block B, the initial momentum of block B went to 0, the initial momentum, the initial kinetic energy of block B also goes to 0, since that initial velocity is 0. And what we're now left with is V1 initial squared is equal to V1 final squared plus V2 final squared. Remember what we were left with from earlier, from the conservation of momentum equation, was, or it's from this one right here, we were left with V1 is equal to V1 final plus V2 final. And actually, I should go ahead and just say this first term is just call that V1 down here. This is just V1 squared rather than V1 initial squared. So we have two equations and two unknowns. We have this equation and this equation, which look pretty similar. It's just the bottom equation has squares on it, the top equation doesn't. When you have two equations and two unknowns, that means you can solve for both unknown variables, which is something that if you would like to take the time to learn it, like I said, you can probably get a perfect score on the AP exam if you want to learn every last little detail. But the important thing that comes out of this is that when you solve these two equations for the two unknown variables, v1f and v2f, what you'll get is that v1f is equal to 0 and v2f is equal to v1. In other words, remember what happened initially. We had v1 initial was equal to v1, and v2 initial was equal to 0. It was initially at rest. Now with the final velocities we've just solved for, we have v1 final is equal to 0, and v2 final is equal to v1. Notice that the velocities, the two objects just basically traded velocities with each other. The initial velocity of object 1 became the final velocity of object 2. The initial velocity of object 2 became the final velocity of object 1. So the shortcut that I want to make sure you absolutely know from now on to make the problems much simpler is, as long as two objects in an elastic collision, if you have two objects in an elastic collision that have the same mass, this only applies for objects that have the same mass, which is actually what most of the problems are going to be, they trade velocities after the collision. Make sure you memorize this, and there will be a question on the next test where you're going to be asked to figure out the final velocities, and as long as you can remember this, it's a very simple way to get to the answer. But they have to have the same mass. This does not work if you have two objects colliding elastically with different masses. So that now tells us that VB, or the velocity of object B, is v1, and the first mass, mass A, is no longer moving. So let's move into the rest of these questions now, which are going to be all conservation of energy. That part that we just did was the only part that involved any conservation of momentum. So part 2, derive an expression for the speed v top of block B at the top of the loop. Since it's just block B moving on its own now, it's turning the kinetic energy at the bottom of the track into, as it's moving through the top, it's going to have both kinetic and gravitational energy because it's a certain height above the ground. So we'll set up the conservation of energy equation as Ki plus Ui is equal to Kf plus Uf. Next thing is to set any terms that are 0. Just get rid of them. So at the bottom of the track, it is moving, so it has kinetic energy. It has no height at the bottom, so we can get rid of that term. At the top of the loop, it is moving because that's where we want to solve for the speed, the v top, and it does have height at the top, so it does have that gravitational energy. So plugging in the formulas, we have 1/2 m v initial squared, which is v1 squared, is equal to the kinetic energy at the top, which is 1/2 m v top squared, the thing we're solving for, plus the gravitational energy at the top, which is mg times the height, and in this case the height is going to be double the radius of the circle. If the radius is r, the height from the top to the bottom of the circle is 2 times that radius. So mg times 2r. All three terms in this equation contain an m, and we're trying to get the v top by itself, so let's move this term over to the left side of the equation. That gives you 1/2 v1 squared minus 2gr is equal to 1/2 times v top squared. We'll multiply everything in this equation by a 2 to cancel out that 1/2. So when you multiply the first term by a 2, the 1/2s cancel out. When you multiply the last term by 2, the 1/2s cancel out. And when you multiply 2gr by a 2, you'll get 4gr. So you can see now that v top is equal to the square root of v1 squared minus 4gr. One thing that I've noticed is still happening a lot on tests that you have to make sure you're not doing is when you get to one of these problems where it asks you to express the final answers in terms of certain things, you have to make sure your final answer is only in terms of what it tells you. And in this problem, if you go back up and read part A, it says express your answers in terms of V1, R, and physical constants. That means there should be nothing else in this equation other than a V1, an R, and physical constants like the G. And that's all we have in here are those terms. All right, part 3, derive an expression for the maximum height that the block can reach. So now instead of comparing this as the initial point with up here as the final point, we're going to compare this initial point with up here as the final point and still use conservation of energy since the track is frictionless. Ki plus ui is equal to kf plus uf. The initial conditions are still the same, so there's no initial gravitational energy, but this time, since we're looking at the maximum height the block can reach, that's when it's reached the point where it cannot travel any higher, so the velocity at this point is 0. So the final kinetic energy we can set equal to 0. So the equations we have are 1/2 mv initial squared is equal to mgh, and we are solving for the h. The m's cancel out, and solving for h, you will get an answer of, just divide both sides by g, that results in vi squared over 2g. Okay, part 4. Derive an expression for the minimum speed v1 that block A can have so that block B can make it around the circular loop without losing contact with the track. So you saw a similar problem to this on the last test with the bucket being whirled in the circle. And the first thing you have to do is figure out what is the minimum possible speed the bucket or the object can have at the very top of the track. So the minimum speed occurs in this case where the normal force becomes equal to 0. That means it's just barely about to lose contact with the track, in the same way that in the bucket problem, at the minimum speed is when the tension in the string was equal to 0. And when you go through Newton's second law, you end up getting V is equal to the square root of G R, the gravitational strength times the radius. I'm not going to go through the setup right now because it's the exact same thing that was on the test. But that's the speed at the top of the loop. That's going to be the V top. So we need to figure out what speed the block can have at the beginning in order to give it that speed at the top. So we're going to set up the conservation of energy yet again. K initial plus U initial equals K final plus U final. At the bottom of the track, once again, the initial gravitational energy is 0. At the top of the loop, it has kinetic energy because it's moving with a speed of square root of GR, and it has the height once again. So we're trying to solve for the initial speed this time. We don't know, there's basically not a V1 now. We're trying to solve for the V1. So plugging in the equations, we have 1/2 m v1 squared, which is what we're looking for, is equal to 1/2 m v top squared plus mg times 2r is the height. Once again, we have the m in every term that cancels out. And we end up with 1/2 v1 squared is equal to 1/2 v top squared. Remember, v top is equal to the square root of gr. So let's replace the v top squared with gr is equal to 2gr. And we want to solve this for v1 squared. So multiply everything by 2. That will cancel out this 1/2. It'll cancel out this 1/2. And it'll turn this 2 into a 4. So the final answer you get for v1 is the square root of, actually that should have been a, that was a plus sign right there. You get the square root of gr plus 4gr, which is the square root of 5gr. Okay, kind of a long problem so far, but now part B we should be able to zip through pretty quickly. It's proportional reasoning, and it's not even proportional reasoning to come up with a new number, it's just proportional reasoning to come up with a new expression. So first thing is, what are the speeds of block A and B after the collision if the collision is perfectly inelastic? When the collision is perfectly inelastic, if two objects have the same mass, that velocity is evenly split between those two objects. And you saw this in the lab demo that we did in class. So for part 1, we can say that both v1f and v2f, which are the same because they're stuck together, is equal to 1/2 of that original speed v1. So the initial speed of both objects is v1 over 2. So it's half, so the speed of object B as well as object A is 1/2 of what the speed of object B was back originally, which was v1. So we're just going to take everywhere where we saw a v1 in some of the previous equations and just replace it with a v1 over 2. So we're going to use, in part 2, we're going to use proportional reasoning on this equation because we want to figure out what is the speed v top at the top of the loop if object B is moving at this speed, v1 over 2. So if I replace this v1 with a v1 over 2, that 2 in the denominator is going to get squared, which gives you a 4 in the denominator. So the answer for that simply becomes the speed at the top is equal to v1 squared over 4 minus 4gr. Nothing else in that equation changed because the only thing that was altered was that v1. And then finally the answer to part 3. So what is the new height the block can reach? So the height we got earlier was v1 squared over 2g. If I replace, and that should be a v1 there, not a vi. If I replace that v1 with a v1 over 2, that 2 is going to get squared again, making it a 4, and that 4 is technically in the denominator, so it'll multiply on with this 2 that's down in the denominator. That gives you a final answer of h equals v1 squared over 8g.